Right, welcome back. Today is week 12, Friday, the 5th of November. The 5th of November, 5th of November, 2021. So now I'm going to explain tutorial 8, question number 7a, and it is from Lay's book in this example, page 311. Now, let's understand the problem first. We are given a matrix A, and then we are told it's eigenvectors. So we do not need to find its eigenvectors or even eigenvalues. It says that it has 3 eigenvectors, v1, v2, v3, and it has 3 eigenvalues. So the first one, 1 corresponds to v1, 2/3 correspond to v2, 1/3 correspond to v3. So what it basically means is that when we have A multiplied by, for example, v1, we would get 1 v1. That means whatever we send in comes out unchanged, right? Maybe let's try to verify that just using MATLAB. So I'll pause now. So I've typed A and I've typed v1. So this little dash is for transpose. So I get -2 to 1. So any value, in fact, I try to put, right? Our favorite 1, 2, 3, we'll get, oh, of course. Oh, what am I doing? I must send any scaled version of v1. So a scaled version of v1 is, for example, 3 times this guy, right? So it is 6, 6, 3, minus 6, 3, minus 6, 6, 3. So you get a picture. So this exhibit that A times v1 equals to 1 times v1. What about A times v2, A times v3? Well, it'll be 2/3. All right, let's try it again. So we have 2, 1. We have 2, 1, 2, which is the second guy, and it'll be 2/3 of 2, 1, 2, which is, let's try, 2 over 3 times 2, 1, 2, exactly the same number. So that's very nice. It shows us that the question is correct. Now, so what? Okay, let's continue. And therefore, we know that AV2 is equals to 2/3 V2 and AV3 equals to 1/3 V3. What we are then told is that this dynamical system, basically it says x of k plus 1 is equals to a times x of k. And of course, therefore, x of 1 is equals to a times x of 0. X of 2 is equals to a times x of 1 is equals to a times x of, a times, and we replace a times x of 0, and therefore we get a squared x of 0. And of course, after 3 times, you should figure out that the pattern is very trivial, and therefore x of k is equals to ak x of 0. So we have figured out that we are interested in this equation in particular. Now, if you try to multiply, so if you want to calculate x100, then you have to multiply a times 100 times, and that's very expensive. Okay, but maybe just maybe we are more clever than that. We can think of it this way. How's that? The easiest way to think about it is that a is equals to, but you haven't figured out this yet, so maybe we have to do it the other way. All right, the other way is let me extract the information from here. In fact, you have to figure out that, fine, not let. Find x0 in terms of V1, V2, and V3. So what does that mean? That means let x0, which is the value given as 1, 11, and minus 2, be equals to some combination. Let's call this C1 alpha 1 V1 plus alpha 2 V2 plus alpha 3 V3. So here's the crux of the problem, Samson. How to find alpha 1, alpha 2, and alpha 3. So basically, if you look at it this way, 1, 11 minus 2 is equals to, this is V1, this is V2, and this is V3. And we have alpha 1, alpha 2, alpha 3. Any problem with this step, Samson? Hello?
Yes, Prof.
Any problem here?
No.
Okay. So what we are saying is that, I mean, from this equation to this equation is nothing but changing the expression into matrix vector multiplication. So we have V1, V2, V3. So only this guy is unknown. Therefore, I mean, then you can solve by Gaussian elimination or any other Gaussian elimination is one way, right, to find it. The other way, of course, is that you can use, you let this guy be called P, okay? P is equals to that 3 vector V1, V2, V3. These 3 matrix, and therefore you, and we know, okay, or actually you have to prove that V1, V2, V3 are what do you call it? Independent columns. Therefore, P minus 1 exists. And therefore, what we have is actually, I'm going to just write it down for you then. X0 equals to P, and let's call this, what do you call that? Some X in the basis of P, okay? So the notation is like this. We have X0, which is this guy. We have P, which is these 3 columns, and we have XP, and therefore X of P is equals to P minus 1 X of 0. Okay, but of course you can just use Gaussian elimination, and we figure out that this value is, so let's compute. All right, let's not be lazy. Do I have my P? P is equals to, okay, let me pause this. Okay, so from MATLAB, I can just do the equations which I have figured out, which is P minus 1 X0 is 213. Let's confirm with Lei. 213. So it is exactly what we said. So basically, we interpret it like this. Therefore, 111 minus 2 is equals to 2 times V1 plus 1 times V2 plus 3 times V3. So this is X0 equals to. Now, when we reach here, we have expressed the input as linear combination of the eigenvectors. And here's the key idea, right? Once we can do that, then we are going to exploit A X0 is the same as A times 2V1 plus 1V2 plus 3V3. And this is become, now, so the jump is here. A times this whole thing is a linear operation. Linear means that we can break it up into individual parts. So A times 2V1 plus A times 1V2 plus A times 3V3. So Samson, is this okay still?
Yes.
Now, so I can bring my 2 out in front, right? Because again, this whole thing is linear. And what about AV1? what does that become? What does AV1? Remember what AV1 is? AV1 is, okay, on top. AV1 equals to 1V1, right? So 2 times AV1 is AV is what? 2 times AV1 is, so here's the interesting thing, right? It becomes V1, okay? Or I mean, if you really want to be very pedantic, then is 1 times V1. Agree? Now the second one, 1 times AV2. This guy becomes, what does AV2 becomes? AV2 becomes 2/3 V2. So let's go down. 1, then becomes 2/3 V2. Agree? So you see, I didn't compute, right? I just look up. And then now 3AV3 is equals to, what's the 3? What's AV3? AV3 is 1/3. It's 3, 1/3 V3. Agree so far? Now, if you have figured the first step, now what about the second step? This is for x1, right? What about x2, guys? So x2 is equals to ax1. So what happened? So I'm just going to a multiply by this whole thing again. Therefore, it's equals to a multiplied by 2v1 plus 2/3 v2 plus 1 v3. And again, you repeat the same idea. So what do you do? After a while, you see the pattern. Oh, all right. I shouldn't jump. All right. Let me not jump. Let's call this lambda 1 and lambda 2 and lambda 3. Okay. So it is 2 lambda 1 v1 plus lambda 2 v2 plus 3 lambda 3 v3. And then what happened? You again 2a lambda 1 and then lambda 1 again. Oh, I think here might be confusing. What is this guy? This guy is, we can bring the 2 lambda out because it's just a constant. So it is a times v1. What is a times v1? Lambda 1 v1. What is whole thing? 2 lambda 1 squared v1. The second guy is a, then we bring the lambda 2 out because it's just a constant, right? v2. What is this whole thing? Lambda 2 squared v2. The third guy, 3 lambda a v3, and the whole thing is 3 lambda 3 v3, and of course this reduces to 3 lambda 3 squared v3. So the pattern emerges, which is therefore x of k is equals to, so this is x of 2, right? Yep. And then therefore x of k is 2 lambda 1 k v1 plus lambda 2 k v2 plus 3 lambda k 3 k v3. All right, let's see Lei's answer. Okay. 2 times 1k, lambda 1, lambda 1 is 1. K v1 plus 1 lambda 1. Did I make a mistake? Oh, yeah, lambda 2 is 2/3. K, okay. Lambda 3 is 3. Lambda 3 is 1/3. Where's my 1/3? Lambda 3 is 1/3. So what am I talking about? 1/3. Lambda 2 is 2/3. And lambda 1 is 1. Can you see the pattern, Samson?
Yes, Prof.
So why do we do all this? Is because we just cheated the system, right? We break the x into sum of linear combinations by lambda, and we make use of the properties of the ax equals to lambda x, and therefore now we don't even need to calculate. We can write the closed form solution. Can you see? Yeah, wonderful, isn't it? All right, let's see the so once we have this equation, then what do you think will dominate when k goes to infinity? When k goes to infinity, this guy remains the same because there's no value of k. K is here, so 2/3 to the power of very large k becomes 0, so 0 times this guy, so this guy goes to 0. 1/3 times to the power of k when k is very large goes to 0, so this guy goes to 0. Therefore, when k goes to infinity, the answer goes to 2 times this vector. Yeah, very nice. Huh? So it converges to a stable point. Okay, let's use our MATLAB and try. Okay, let me have my let's have our A first. Where's my A? A is this the correct? Yeah, this is the correct value of A. To verify A times 9, I should get exactly the same value. Yes. So now A times A times, so A times A, I get this. A squared, I get the same value. So A to the power of 100 is fine. A to the power of 100 times who? What's my X? 111 minus 2. 111 minus 2. And the answer is, whoa, cool. Minus 442, right? So we got it figured out. Yep, the answer is correct. Okay, so I will pause now and take questions. So the question now asks, why can we express x naught as linear combinations of these three guys, right? Now what is this three guys? These three guys is a basis. We are in the space of R3. We are in R3, so x naught belongs to R3. Yes, and this is three bases. This is, sorry, not three bases. This is a basis for R3. Each of these guys has three elements, right? B1, B2. First, the number of elements in B1 is 3 elements. Yeah. And then, therefore, and then each one of these three guys are independent of each other. Okay, so let's call him P. So we then say we are now finding the linear combinations of these three vectors to make up this guy. So this is the classical problem that you have, right? Which is, I mean, your original problem from tutorial 1 is always AX equals to Y. Now Y is your now 111 minus 2. Can you see that? And your X is now your alpha 1, alpha 2, alpha 3. And your A is given to you, which is that. Where's my A? Oops. All right. So he just represented the whole thing differently. Minus 2, 2, 1, 2, 1, 2, and 1, 2, minus 2. Minus 2, 2, 1, 2, 1, 2. Okay, so can you see it's the same problem, just cast differently? He tells you I have 3 eigenvectors. I have an unknown x0. So this is the 3 eigenvectors. The P is the eigenvector. I have my unknown x0. Okay, that's why maybe it's that when the notation change, right? You guys get confused. So now your A is these eigenvectors. Your Y is this guy. And the only unknown is this guy, right? Because when we want to find a linear combination, when you open up this equation, what is this? This is equals to alpha 1 times minus 2, 2, 1 plus alpha 2 times 2, 1, 2 plus alpha 3 times 1, 2 minus 2 and equals to 111 minus 2. Can you solve this equation? Yes, you can. They will be unique because when you reduce this matrix by Gaussian elimination, there is no free variable. There will be 3 pivots. Okay, so does that answer your question, Jonathan? Okay. Samson?
Yes, Prof. Thank you.
Okay, I'll pause recording now. So I guess, right? I guess maybe it is non-trivial to follow because we understand it originally from ax equals to y, and now we are asked, to solve the whole thing, but the variable names have changed, so that's why maybe we couldn't follow. But this is the basic idea. All right, so I'll pause now and I will start a new page. Change of basis. And in the part 1 of this course, you have seen the change of basis. Basically, in the change of basis is we have an element x in the vector space. Now, so we are going to try to understand something called a change of basis today. Typically, we write our column vector x without this square thing and a b below, or square thing with a c below. So what does the square thing with a b and a c below? It means that we are representing the x vector in the b coordinate in xb. And xc means we are representing our x vector in the c coordinate. So what does it mean? All right, let's see the picture here. This is a R2 problem. XB means move 3 along the B1 and 1 along B2. So B1 is this blue line here, and B2 is this blue line that is going up a little bit here. So you can see B1 and B2. Now the origin is always fixed. The origin for any basis is the same. So this is the B basis and this is the C basis. They are representing the world in just different bases, but look where the origin is sitting, and the origin sitting, if you take this figure and overlap with this figure, they will meet. Now this is X. Here is also X, but they are represented in two different bases. One is B basis, and we say this X is in the B basis is 3, 1. Actually, I would rather you write 3, 1 than a little bit B below, okay? So that we can see. Otherwise, you will forget this 3, 1 belong to the B basis. 3, 1. What does 3, 1 means? 3, 1 means move along B1 by 3. So B1, 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 3 times of B1. And move 1 along B2. So remember, a basis is independent vectors that spans the space. So therefore, the B basis is actually, is B1 and B2. And it will move. So B1 is something that moves along here. So it has two components. What is B1? What is these two components? Actually, from this diagram, we can't figure it out. Oh boy. And what else? Okay. Now, but you guys have already figured out that to reach X, we move along 3 times B1 and 1 times B2. Now, if you live in the C coordinate world, to reach X, he gives you the answer is 6 times C1. This is a C basis. So we move along. So this is C1 here and C2. Now, the bases are arbitrary, up to you to define. As long as you have two independent vectors for R2, they can form a basis. The definition of a basis is a set of independent vectors that spans a space. So we have C1, C2 spanning R2. We have B1, B2 spanning R2. They can be bases. XC moves to use XC 6, 4, meaning we move 6 along C1 and 4 along C2, reaching the same point. Look, here and here. So first is they must start at the same origin, otherwise it doesn't make sense, right? And now we use different bases to reach the two different places, to reach the same places. Now, the question is, if we are given the basis B and the basis C, then how to find one with respect to the other? Okay, that's the question. So I'm going to try to do this with you today. Right. Let's have a concrete example. Now, I will give you X as 2, 3. And I'm going to ask you to find X in the B basis and X in the C basis. To do that, I must give you the set of B. And the set of B is maybe 1, 1. And the set of the second basis is 0, 1. And what about C? 1, 0, minus 1, 0. Oops. Minus 1, 1. So the important thing is that these two guys are independent. So it's obviously they are independent. They cannot be formed by the other guy or linear combinations of many of the other guys if we are in more R3, R4. And this is C2, oops, C1 and C2. Then of course we typically write, like, instead of writing it as a set, because we are going to manipulate it later, we write it as a matrix. Okay. All right. So we have figured out what is X. We know the basis B. So what does it mean? All right. The key equation to remember is this. If I give you the X as a coordinate, then I'm actually telling you X, the standard basis. What is the standard basis? It is, the standard basis is typically called E, and E is 1, 0, 0, 1. In fact, it is always the identity matrix. Okay. Okay, and the standard basis is E. All right, and then if I have given you X, that means I have given you X in the standard basis if I never tell you anything else. And then the key equation is equals to B X B C X C. Now, if you can remember this equation, that's it. Then you can convert into any basis that you like. Therefore, X of B is equals to B minus 1 X of the standard. And then if you're lazy, B minus 1 X. That's it. And X of C, C minus 1 X of standard, C minus 1 X. Then from what do you call that? From B to C, from XB to XC, what do we do? Right? So you cheat, you take this equation and you observe. These three things equals to each other. Therefore, I want to express X of C. Therefore, all I need to do is I move my C across the other side. So therefore, it is X of C is equals to C minus 1 B X of B. Why? So from B X of B equals to C X of C. Now, B and C are bases. Therefore, their columns are independent. And if we have a full set of bases, full set of independent columns spanning, let's say in this example is R2, then that means we have two columns. So these two columns, V1 and V2, and therefore we have a 2 by 2 matrix. And since it's a 2 by 2 matrix and their columns are independent, therefore they are invertible. And therefore C and B are invertible. And therefore, if I want to get XC, so I do C minus 1B, XB, C minus 1C, X of C, and this reduces to I. And then we have this equation here. Okay, and of course the other way around. So now we are playing with change of basis. Okay, so this is the first equation that you need to know. This is the second equation that you need to know. C minus 1B, X of B. So this changing from B basis to C basis, and the other way around, you can find it out yourself. Right, I'll pause now and take questions. Okay. Why am I so confused? So you can refer to, there are two places I will refer to, and I will show you. Tutorial supports. Okay. All right, the last idea that I will leave with you is this. I am in now page 2, page 3. So I have the equation that you really need to remember is this: X standard equals to, in this way, is the B basis multiplying by XB. And X standard is the same as the C basis multiplying by the X in the C basis. That's the key idea. Now, once you have figured that out, then what about the other way around? The other way around is, since B and C are matrices and they are invertible, therefore B times X standard is equals to B times B minus, B minus 1. B minus 1 times X standard is equals to, I'm taking this equation here, B minus 1 times the original guy, XB, and this reduces to X of B. So now I have figured out how to reach XB from X standard by pre-multiplying by B minus 1. So in fact, I always get myself confused. So I resort to writing all these equations down. And therefore, C minus 1 X of standard equals to X of C. So you just write these 4 equations down first. Now, what about from B basis to C? What should I do? So if I've given you only X of B, and I want you to represent not to X of standard, but to X of C, what should you do? So in fact, the trick is always to do this. Just change it to the standard and then change it to C. So remember, what is X of standard in terms of B? So I write down. So X standard is nothing but B times X of B. Then what about X of C? X of C is equals to C minus 1 times this whole guy. B times X of B. Right, this guy is the X standard. So X of C is equals to C minus 1 B X of B. So X of C is equals to C minus 1 B X of B. Now I'm going to ask you to draw these lines here and figure out something. This is in X of B. What is this guy? B times X of B changes. B times X of B. B times X of B changes X of B to standard basis. So this guy is already, so I'm going to draw it in red now. So this guy is already in the standard basis. In the standard basis, I want to change to C. What do I do? So if I in the standard basis, I want to change to, sorry, in the standard basis, I want to change to C. I apply this equation here. Is it?
Could you shift it to the right a bit? We can't see the full equations.
Sorry. Okay.
Thank you.
Yep, no problem. C minus 1. Oops. Sorry. Yeah, you see, I'm always confusing myself. So I'm already in the standard basis, and I want to change to my C coordinate. So I prim out left multiplied by C minus 1. So this last bit changes from standard to the C basis, because this is what I want to get. All right. Now, yeah, you guys have to go and write this down one by one, and then don't get confused. And then after a while, you realize that it's nothing but, all this simple linear, this algebra, right? This is really algebra, moving things around. Okay. Now the key takeaway is B and C are bases. If they are square, then they are invertible because they are independent, and therefore I can manipulate all this manner. So now it looks very cool, very complicated. But it just comes from these three equations, really. All right, so this is the change of basis. And then if you are going to ask me, how does that relate to eigenvalue and eigendecomposition? So finally, I will show you the last slide today. 4. Now, A is square, can be diagonalized, and it can be diagonalized. Meaning A times, it has a full set of eigenbases. Okay, what does this mean? For example, P1 equals to lambda 1 P1. So let's only play with two guys. Therefore, and so I have A, P1, P2. This is the same as A. So what is this the same as? It is the same as okay, so far. So this is A times P, P times D. So therefore, D is diagonal and contains the eigenvalue. What is P? P are the two eigenvectors in this 2 by 2 problem, in this 2 by 2 matrix A problem. Now we have figured out AP equals to PD. Therefore, A, now what is P? P is a set of eigenvectors, and each eigenvector is column of length 2. There are 2 of them. They are independent of each other. Therefore, p minus 1 axis. So I'm going to multiply by p minus 1 on the right. This guy goes to I. A reduces to PD, p minus 1. Right? Now, when you see this is very close to what we want already. This is always the equation that we show you. And then now we say y is equals to ax. Therefore, we will replace a by PD p minus 1x, correct? Now, this is beautiful. Look at this. What does this guy do? Changes x in the standard basis to p basis. What does this guy do? Perform the transformation A in the p basis. And what does the last guy do? Convert the y in the p basis to y in the standard basis. So you have to figure this out by yourself. All right? P minus 1x times d times p. Where is all this happening? You already seen it here. Yeah, you've already seen it here. Of course, the sign are inverse, but you get what I mean after a while. So you have to go through this. I will record the last lecture and try to explain this in more details, but you get the picture here. Okay, and with that, I will now pause.